Welcome back. In this video, we'll be looking at example 7.4.3. I'm going to consider this set of three vectors in R3, and I'm going to look at its span. I want to know if the original set A is a basis for its span. Alright, so if you remember what we did in the last video, we defined basis. There were two conditions. First thing I needed is that B spans S, and then I'll also need to check that B is linearly independent. All right, so let's start with the first one. That will be quick in this case. So condition 1. Is A a basis for S? So A must span S. Well, that's true. In fact, in this case, it's given. S is span of A. So nothing much to show in this case. So let me move on to condition 2. So in condition 2, I must show that, or wonder whether A is linearly independent. And if you remember what that means, I'm going to look at linear combination of my three vectors and see how many ways there are of writing 0. So I'm going to look A1 times my first vector plus A2 times my second plus A3 times my third, and I want to know how many A1s, A2, A3 work in this equation. As soon as one work that isn't 0, 0, 0, they're dependent. If I need to put 0, 0, 0, that's the only way of making this equation true, then they're independent. All right, so if I try to solve the system, I'm going to have my coefficients for A1 come right here, my coefficient from A2 come here, and the one for A3. So notice that actually I have my first vector comes here, my second one comes here. That was one of the things we noticed before. And then I'm going to reduce this. I've done it for you. So I'm going to start nicely, but then something's going wrong. The third column is free. And so I have a free variable, which means I have infinitely many solutions. Infinite many solutions, that means not only the trivial, so A is linearly dependent. And so A is not a basis. The first condition was right, second condition isn't. So A is not a basis for S. All right. So now I want to go back a bit to section 7.2. Since we are in R3, we have more information, more control over what's going on. So I want to describe S geometrically using the method of section 7.2. So let me give the names to these vectors. Let me call the first one V1, the second one, that's going to be V2, and the third one is going to be V3. So when we looked at the span of three vectors in R3 in section 7.2, we needed to ask ourselves, are those three vectors 0? Well, they're not. Second question, are they parallel? So let me check that by using the cross product of the first two. So if I do the cross product, up, 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 what I will get, minus 1, 1 plus 1, sorry, this is 2. 1 plus 1, and then 2 plus 1, that's 3, minus 1 plus 2, that's 1. So this isn't 0, so that means they're not parallel. So I don't have the 0 vector 3 times. The vectors I have are not all parallel. So at this point, it's either a plane or R3. It's going to be a plane if they're coplanar. So let me check that with the triple scalar product. Of course, you could do it in any, you could put the vectors in any order. I'm just going to do that one because I already have this cross product here. So 4 minus 3, 1, dotted with 2, 3, 1. I get 8 minus 9 plus 1. I get 0. So because I get 0, I know that V1, V2, V3 are coplanar. I have coplanar vectors. They're not parallel, so S is a plane in R3. As usual, because it's a span, it contains the origin. All right, so because we're in R3, we have a lot of tools. We have those products, and we can tell that S is the plane in R3. But now let me move on and let me try to find a basis for this plane. So I want to show that this set of two vectors is a basis for the span of my A above. So if you notice what I've done, I've gotten rid of the third vector. That was the one that was giving me trouble. That was the one that was giving us this free variable here that was stopping us from having a linearly independent set. So I want to prove this as a basis. I'm actually going to start with condition 2. And then I'm going to do condition 1, just because condition 2 is in this case a bit faster, and it shows you why we got rid of that extra vector. All right, so now I want to consider A1 V1 plus A2 V2. They're the same vectors as before, so this one was V1, this one was V2, equals 0. If I put that in a system, I'm going to get the coefficients of A1 first, the coefficients of A2, then 0 constants. And if I reduce that, this is what I'll get. I have no free variables. I have no inconsistent row, of course, because the system is homogeneous. That means a single solution. A1 equals A2 equals 0, and so B is linearly independent. So we have checked that B is linearly independent. All right, so now I need to show that if I only use these two generators instead of all three, I get exactly the same set. Right? It seems easy, and you've kind of done it before, but it's a bit more tedious than you would expect. So let me show you how I would how I would show this, and then in the future we'll have a shortcut here. So claim number 1. First thing I'll do is I'll show that this V3 is already in the span of B. So V3 is in the span of B. All right, so I want to write A1 V1 plus A2 V2 equals V3. And if I try to write this, I'm going to start with the coefficients of A1 in the first column, coefficients of A2 in the second column, and then my constant is going to be that V3 here. So that means 4 minus 3, 1. And if I reduce this, you may think I'm actually cheating and using magic here, but the only time I've actually used a computer algebra is here. From this reduction, I could get everything we've done so far. So the matrix I'm trying to reduce now is this one without the 0. And so if I use exactly the same row operation, I'm going to get this one without the 0. So here what I get 1 0 0 0 1 0, and then I get 2 1 0 as my constants. And so that means V3 is equal to 2V1 plus 1v2. If you're not sure you've done this right, you can always check. It's not too hard to take that linear combination here. So twice times, yeah, plus 2 is 4, yeah. And so, yes, v3 can be written as a linear combination, and so v3 is in the span of B. All right, so now that's done. I'm going to show that if I take the span of B, which is span of v1, v2, that's the same as A, which was the span of v1, v2, v3. And so span of B is S. All right, so I'm going to take W in the span of the two vectors. So I'm taking W here, and I want to show that it's in this set as well. So W, it's in the span of two elements. That means I can write it as a linear combination of these two. So A1 V1 plus A2 V2. And now to show that it's in the span of A, I need to write it as a linear combination of these three. Well, that's not so hard. All I have to do is kind of stupidly almost add 0 times V3. And so I'm going to still be able to build W even if I'm given an extra generator, right? That doesn't hurt. All right, so everything that's on this side is in that side. Now we're going to take the other direction. So let's call it W again. I'm going to take W in the span of V1, V2, V3. That is S. So anything in S, then W, it's in the span of these three, so I can write it as a linear combination. I want to write it as a linear combination using only V1, V2. I want to show that I don't need to have V3 as a generator. So I'm going to use this equation we found here, and I'm going to replace V3 by it. So that will be A1 V1 plus A2 V2 plus 2 V1 plus V2. That's my, that's my V3, but I need A3 in front. All right, so if I just use algebra here, I'm going to get something times V1. If I put all the V1s together, I get A1 plus 2A3. And if I put all the V2 together, I'm going to get A2 plus A3. I've written this arbitrary element of S of that side in as a linear combination of V1, V2. That means all right, so the two sets have exactly the same element. And so we've proven that span of B is span of S. So that's condition 2. Right, so we've proven that B is linearly independent. We've proven that span of B is span of S. And so we have the two condition. B is a basis for, oh, sorry, not span of S. Well, I guess, sorry, I meant span of V1, V2, which is S. Sorry. So B is then a basis for S, and that's what we wanted to prove. All right, So this was an important example. It was the first example in a long series of things that we'll do that will be similar. So what I'll do is in the start of the next video, I'll kind of recap what I want you to take away from this example so that we don't have to do all of this work every single time, right? All right, good. So I'll see you next time.